Hey, welcome to The Explainer. Today, we're tackling one of the absolute giants of modern science, the Schrödinger equation. We're going to break down what it is, why it's so important, and I know a lot of you are waiting for this, how to nail the perfect exam answer on it. So yeah, let's just dive right in.
Okay, so picture this. Physicists had just wrapped their heads around this totally wild idea called wave-particle duality. The fact that tiny little things like electrons could act like a solid particle and a spread-out wave. Mind-blowing, right? But it left this massive question mark just hanging there. I mean, if an electron can be a wave, shouldn't there be an equation that describes that wave? There had to be. But what was it?
And look, this wasn't some tiny little detail they could just ignore. It was the missing piece of the whole quantum puzzle. They had all these amazing ideas floating around, duality, the uncertainty principle, but there was no single mathematical framework holding it all together. It was like they'd laid the foundation for a house but had absolutely no blueprints to build the rest of it. They were kind of stuck.
And then, in comes our hero. 1926. An Austrian physicist named Erwin Schrödinger steps onto the scene. And he doesn't just have an idea, he proposes this absolutely groundbreaking equation that, well, it didn't just answer the question. It basically became the bedrock of quantum mechanics, period.
Okay, so what is this legendary equation? Let's peel back the curtain a bit and see what it actually does, and maybe even more importantly, get the big picture idea of where it even came from.
All right, so at its core, the Schrödinger equation is basically a rulebook for how a quantum particle behaves. You know how Newton's laws can tell you where a planet's going to be in its orbit? Well, think of this equation as doing the same thing, but for the weird, fuzzy quantum state of an electron as it zips around and changes over time.
So what's the whole point of solving it? What's the prize at the end? It's something called the wave function. You'll see it written as this cool-looking Greek letter psi. Now remember that symbol. Seriously, lock it in your brain, because figuring out what psi means, that's the key to this whole thing. Okay, now for all my students out there, lean in for a second. This is a big tip. You almost never have to reproduce the full, gnarly mathematical derivation in an exam. Phew, right? What they want you to know is the concept, the big idea, and it's actually pretty elegant. Schrödinger basically started with the simple classical equation for total energy. Then, and this was the genius part, he swapped in some bits and pieces that describe waves. He mashed it all together, did some simplifying, and voila, out came his revolutionary equation.
Another super important thing to know is that there are two main flavors of this equation. You've got the big one, the time-dependent equation. That's the full-fat version. It describes how any quantum system changes over time. But the one you're probably going to meet in your exams is its simpler cousin, the time-independent version. It's used for special cases, like finding the fixed, stable energy levels inside an atom. It's your go-to tool for a lot of textbook problems.
Right, so the equation spits out this wave function, this psi. But what on earth is it? I'm not going to lie, this is the most important and, frankly, the most brain-bending part of the whole topic. So let's really dig in.
Yeah, what does psi actually mean physically? When we go through all that math and find it, what have we really discovered?
Okay, get ready for this, because it's a weird one. By itself, the wave function psi has no direct physical meaning. Nope, you heard me. All that work, solving this monster equation, and the answer doesn't actually correspond to anything you can poke or measure in the real world. So, what was the point of all that?
Well, the point, and this is where the real genius comes in, isn't about the wave function itself. It's about what you do with it next. The secret gets unlocked when you stop looking for certainty and start thinking about probability.
Here's the trick. You take that wave function, psi, and you square its magnitude. What you get is something called the probability density. And that has a very real, very important physical meaning. It tells you the probability of finding the particle at a certain spot. See the difference? It doesn't say the electron is right here. It says the electron is most likely to be found right here. And this is a huge departure from old-school classical physics. We're throwing out the idea of definite, certain predictions. We're entering a world that's run by statistics and likelihoods. It means the universe, at its very core, plays a game of chance. So why should you care about all this probability stuff? Because this one equation lets us do some absolutely incredible things. It's how we calculate the exact energy levels in atoms, which is basically the foundation of all chemistry. It's how we understand the structure of atoms. It even explains super weird quantum effects like tunneling, which, by the way, is the reason the transistors in your phone and computer even work. Let me put it this way. Without the Schrödinger equation, a huge chunk of modern science and technology, physics, chemistry, electronics, it just wouldn't exist. It is that foundational to the world we live in today.
Okay, let's switch gears and get super practical. For everyone studying this stuff, how do you take all this mind-bending theory and turn it into a killer full-marks exam answer? I gotcha. Let's lay out the game plan.
Here it is, your 5-step checklist for a perfect score. 1. Start with the definition. What is it? 2. Explain the idea behind the derivation. Remember, total energy meets wave properties. 3. Write down the actual equation. 4. Don't forget to include the time-independent version and say why it's useful. And 5. The grand finale. Explain the physical meaning of psi squared, the probability density. Follow that roadmap, and you are golden.
You know, there's this great analogy that I think just nails it. If discovering wave-particle duality was like finding a door to a completely new, bizarre reality, then the Schrödinger equation was the blueprint that allowed us to build the entire house of quantum mechanics. And it's a house we're all living in right now.
So that leaves us with one last really cool question, right? We've got this master equation, this blueprint for the quantum world. What actually happens when we use it to solve real-world problems? Well, we're going to get into some of those specific solutions in our next explainer. See you there.